All right, perfect. Well, thank you for joining, everyone. My name is Luane Bandunas, and I am the publisher for the journal JWPE and Desalination. And I'd like to welcome you to today's webinar. I'm just going to give a brief introduction of the two journals, and then we can get started with our speaker for today. So Desalination publishes high-quality research on desalination materials, processes, and related technologies. It's got an impact factor of 8.3. It has an acceptance rate of about 29%. And in the last 12 months, the journal has received just over 2,760 papers and has published just under 900 papers. Here you can see the citations that the journal gets, over 26,000 and over 2.4 million article views or downloads. And here are the two editors-in-chief. They're also on the call, Professor Tao He and Professor Ha-Kyung Shon. So I'm sure if you have any questions, they'd be happy to answer them. Then the next journal is Journal of Water Process Engineering. It has an impact factor of 6.3. You can see over the last 12 months, the journal received just over 6,500 submissions and has published just over 1,820 papers. It's received over 31,000 citations and over 1.8 million article views or downloads. And our two editors-in-chief are Professor Xiaochang Wang and Dr. Ludo Dumi. Professor Wang is also on the call, and Dr. Dumi will be joining us shortly. So there are various outreach activities that both journals do. They both have social media presence, LinkedIn, WeChat, where they promote activities and really interesting papers. For JWPE and Desalination, we now have a joint webinar series. For JWPE, we recently had a 3-minute thesis pitch event aimed at PhD students where they presented their thesis in 3 minutes, and we will be announcing the winners of that event at the end of this webinar. We also have editor's choice papers and highly cited papers that are promoted on social media. For JWPE, we currently are calling for applications for the Trailblazers Award, and this is aimed at mid-career researchers. So please do apply if you're interested. And both journals publish special issues on on hot topics. Now, the webinars have been running since March 23, and here you can see a number of speakers that we've had coming from all over the world and on various topics. And as I mentioned, we are co-branding this webinar series now between JWPE and Desalination as from September. And this was the 3-minute thesis pitch event that we had, and we will be announcing the winners of that shortly. So thank you very much. I'm now going to hand over to Professor Shon, Professor He, who will be announcing and introducing our speaker for today.
Thank you, Luan. Welcome everyone for joining our first Desalination webinar. This is a new experiment of Desalination Journal to digest a recent scientific discovery in our field. Right now, we are organizing this event together with our sister journal, Journal of Water Process Engineering. I would like to thank Luan to help with everything. I'd like to thank Professor Wang and Ludo for agreeing with our participation. I would like to thank Sean for helping this event. I'm sure we will continue this event to improve the impact of desalination worldwide. Before start of Razi's presentation, I would like to give a brief intro of his background. Razi had his education at Ben-Gurion University and PhD at Technion. After his PhD, he joined Yale together working with Professor Manny for his postdoc. He is now working at Technion as assistant professor. Razi published more than 50 papers on membrane processes for selective separation. molecular transport and selectivity in membrane and nanopores, biologic processes for water and wastewater treatment. He will give us today an overview of his very recent interesting research on transition state theory and transport mechanism of ions in nanofiltration membranes. Now, welcome, Razi. Thank you. The floor is yours.
Okay, thank you very much, Professor E, Professor Sean, Professor Wong, and Luane, for inviting me to give a talk here. I will just share my screen. So, can you see my screen?
Yeah.
Okay. So, as the professor has said, I started my lab at Technion 5 years ago in October 2019. And the focus of the research in my lab, as he mentioned, is to explore and understand molecular transport and selectivity in mostly in salt-rejecting membranes like reverse osmosis and nanofiltration membranes. And based on the insights that we gain, we try to develop new membranes with improved selectivity. So in the coming presentation, I will talk about the application of transition state theory to explore transport and selectivity in mostly in nanofiltration and reverse osmosis membranes. So, of course, I will give a brief and basic introduction of transition state theory. Then I will connect it to membrane transport, to membrane permeability. And I will also give some examples of how we can use this theory to better understand the transport mechanisms. And I will also dedicate a significant portion of the presentation to introduce the challenges and difficulties and maybe even problems that we should be aware of when using this theory. And one last important note before I start. So Israel is in a war now, and there is a rocket attack from time to time also on Haifa, where Technion is. So if there is a rocket siren, I will need to go to a safe room and stay there for 10 minutes. So don't go anywhere, and I will come back. Hopefully, it will be quiet during the presentation. So now I can definitely start. So we'll start with a quick, relevant background. And more specifically, let's talk about salt-rejecting membranes. And let's start with talking about reverse osmosis, which has very tiny pores in the size of a few angstroms, which is the scale of a water molecule. So these very tiny pores, they allow almost complete rejection of salt or other solutes. So in reverse osmosis membranes, we actually get a very good, very high water salt or water solute selectivity. On the other hand, we have nanofiltration membranes with slightly larger pores that allow the selectivity not only between water and salt, but also between two salts or two solutes, okay, what we call solute-solute selectivity. As you can see here in the illustration, selectivity between a purple sphere and an orange sphere. And this solute-solute selectivity is most commonly or best explained by two main mechanisms, size and charge effect. So intuitively, smaller ions or molecules will penetrate better through the membrane pore. And because our membranes are charged, so they can also repel electrostatically co-ions or ions with the same charge. So based on these two mechanisms, we can actually achieve selectivity between species molecules that differ in their size or their charge. And one noticeable example for this kind of selectivity is monovalent divalent ion selectivity. So you can see here on the figure on the left, you can see the observed rejection of divalent ions in green and monovalent ions in red for different membranes, nanofiltration and reverse osmosis membranes, of decreasing pore size when we go from left to right. So first of all, you can see that the rejection of divalent ions is higher than that of monovalent ions. And this is mostly because of the larger hydrated size of divalent ion and the stronger hydration shell of divalent ions compared to monovalent ions. So this is one observation. And we can also see that for the NF membranes, the divalent and monovalent groups are more distinct, which means that we can achieve better selectivity due to the reasons that I just mentioned. But this selectivity is relatively rough, okay? It's not so high, and also it's not ion specific, okay? So it's only selectivity between groups. So if we want to increase the selectivity and maybe even obtain an ion specific selectivity, we will probably need to leverage some more specific mechanisms beyond just size and charge effects. And one important evidence for the existence of such additional mechanisms is perhaps the consistent selectivity trend that we often observe between molecules or ions that have similar size and charge, like the case of monovalent anions. So we can see here chloride, bromide, and nitrate. They all have, of course, a charge of -1, and they also have similar hydrated size. So they are almost identical, but we still observe a consistent selectivity trend between these ions. So we can see that chloride rejection in red is always higher than bromide rejection, and bromide rejection is higher than nitrate rejection. So again, this trend suggests that we can find some other important mechanism beyond just size and charge. And one of the main problems to explore and understand these additional mechanisms is the fact that current models have are very limited to elucidate this mechanism. So, for example, if we take the commonly used solution diffusion models, so if we follow the mathematical development of this model, so eventually we end up with two important formulas. One that describe the water flux, and the other that describe the solute flux. But anyway, the flux or the transport is according to the solution diffusion model, is a function of the driving force, okay, either a pressure gradient or concentration gradient, and a single parameter, okay, the water permeability or the salt permeability. So if we want to elucidate and to better understand the selectivity that we get between species, so we are actually limited to the measurement of B values, okay? So we can only measure B values for two solutes and then see the differences between them and try to assume why we see this difference. So actually we want to better understand this B value, what we have inside. And this is maybe where transition state theory can help us. So in the coming slides, I will introduce the basic of transition state theory, and then we will talk about how we can use it to maybe better understand the transport in membranes, in nanofiltration and reverse osmosis membranes. So let's start with introducing transition state theory, and it was actually Arrhenius in 1881 that first coined the term activation energy. Okay, so according to Arrhenius, when reactants are transformed into products, they need to go through a high energy, unstable state. And based on this idea, Arrhenius formulated this well-known Arrhenius equation that actually connect the rate constant of chemical reaction to the temperature, okay, through two main parameters, the activation energy, you can see in green, and the pre-exponent factor. And this equation was very successful in predicting the reaction rate for many chemical reactions, but the physical origin of these two parameters was not clear at that time. So in the coming years, a very large scientific effort was initiated to try to explain these parameters, okay, the physical origin of these parameters. And these scientific efforts culminated after more than 50 years in 1935 in what we call today the transition state theory. So according to the transition state theory, the energy of any solute or molecule, okay, can be described as a potential energy surface, which actually describes the energy of the molecule as a function of its fundamental properties. So as you can see in this example, we can see the energy of I think it's of hydrogen, okay, as a function of the bond length and the bond angle between the two hydrogen atoms. So on this potential energy surface, we can find both the reactants and the products of the reaction. And when the reactants are transformed into products, okay, they actually, according to transition state theory, they choose the easiest, okay, or the shortest path, okay, and this path crosses what we call the saddle point, okay, which is actually the transition state. So if we know, using complicated methods, we know how to measure, because we know how to build the potential energy surface, so we can also measure the energy of the transition state, okay, so we can measure the entropy and the enthalpy, and therefore the Gibbs energy, the Gibbs free energy of the transition state. So if we know how to measure this energy, and assuming that there is an equilibrium between the transition state and the reactants, okay, in this case, we can actually describe the rate constant as a function of the entropy and enthalpy difference between the transition state and the reactants. So, and this theory was formulated by Ehring in 1935, Ehring and co-workers, and this theory, okay, actually, so it provides a physical explanation for the transition states, okay, because it explains what it is and where it is exactly on the potential energy surface. So this is one thing. And the second thing, that it can explain the pre-exponent and the activation energy from the Arrhenius equation in terms of entropy and enthalpy changes. Okay, so we now understand the basic of transition state theory. So now let's connect it to membrane permeability. So in theory, transition state theory can be applied to any elementary chemical reaction. Okay, and diffusion, okay, is also considered an elementary reaction, because in diffusion, a solute needs to detach, okay, disconnect itself from neighboring water molecules. Then it goes into an high energy unstable state, and from there it can move forward and stabilize itself in the next coordinate. Okay, so diffusion is basically a thermally activated process and can be also described by transition state theory. Now, when we talk about transport in membranes, so it's a problem of multiple diffusion jumps in series, because the solute needs first to partition from the water into the membrane, and then it needs to face several barriers inside the membrane in series, and then partition back to the product side. So it's a problem of multiple energy barriers in series, but according to Ehring work from 1949, so it was a later work that connected his original theory to membrane permeability. So according to this work, the intrinsic permeability, okay, which equals to the partition coefficients times the diffusion coefficients, can basically be simplified to a single barrier problem, and therefore mathematically can be represented by a simple Arrhenius type equation, as you can see here, and the energy term in this case equals to the summation of the energy barrier for diffusion, ED, inside the membrane, and the energy of partition, which represents the energy difference between the state of the solute inside the membrane and outside the membrane. Okay, so permeability in membranes can be described by transition state theory and by a simple Arrhenius type or A-ring type equation, and we can also measure the activation parameters relatively easily by experiments. Okay, we can measure it experimentally. So this is the permeability that is represented by an Arrhenius type equation. Now, if we show the natural logarithm of the permeability as a function of the temperature reciprocal, okay, so we can actually extract from the slope of the curve, we can extract what we call the effective energy barrier, okay, the energy term, and from the intercept, we can extract the pre-exponent factor, and we can apply the same methodology for the more detailed A-ring equation. And in this case, we will extract from the slope the delta H, okay, the difference, the enthalpic barrier, and from the intercept, we can extract the entropic barrier, okay. So we know that now that we can use transition state theory to describe permeability, and we can even measure the activation parameters. So the next question is actually, okay, so how does it help us to better understand the transport? Okay, so the first simple answer is that now, if we measure instead of measuring just the B value that describes the permeability of a solute, now we can actually break down the permeability into two components, okay? An entropic component and an enthalpic component. So if we break down one thing into two things, we can already understand things better, okay? But if we want to be more specific, so let's try now to give interpretation to these two terms, the entropic and enthalpic terms. And I must say, before I give this explanation, that this interpretation is relatively complex and it can be very tricky sometimes. So my following explanation is a simplification of reality, just to introduce the main concept. Okay, so let's try to first to understand what the delta S or the entropic barrier, what does it mean in terms of mechanisms? Okay, how can we understand better the mechanisms by knowing the delta S and the delta H? So let's start with the entropy, and let's take the example of a membrane, okay, polymeric membrane with pore size distribution, okay, and two solutes, small solute and large solute that try to penetrate the membrane. Okay, so if we remember the definition of entropy, so entropy represents the freedom of motion, or the number of accessible microstates. So it is obvious that in this case, the small purple sphere will have more possible microstates to occupy inside the membrane. It will maybe have some more freedom of motion to move. So we can say that the entropic barrier for the purple sphere is lower than for the orange sphere. Okay, so this is one intuitive explanation of the entropic barrier, the freedom of motion, or the number of possible microstates. So now let's try to add also the enthalpic barrier. And if we connected the entropic components maybe to steric effects and to freedom of motion, so it is convenient to connect the enthalpic term to interactions with the environment. So to exemplify this, let's assume that now that the purple sphere is negatively charged, and also our membrane is negatively charged. So again, it's obvious that it will be more difficult for the purple sphere, okay, to enter the membrane, or in other words, the enthalpic barrier of the purple sphere will be higher compared to the orange sphere, and we will need to take it into account so that eventually, okay, less a purple sphere will be able to penetrate the membrane. So in total, you can see here, we got 3 purple spheres in the membrane and 2 orange spheres, which means that actually the permeability, the B value of the purple sphere will be probably higher, okay? But now, using the enthalpy and entropy components, we can try to give some explanation why the B value of the purple sphere is higher. So this was a kind of a simplified explanation of the delta S and delta H terms. And in general, I can summarize this part by saying that if we have a difference in the Gibbs free energy of activation, delta G, for 2 solutes, so we will have selectivity between them. Okay, so you can see in this figure, if the blue sphere has lower free energy of activation compared to the red sphere, so its transport rate will be faster. Okay, and we will have more blue spheres in the product. And I think the best example for how the activation energy or the Gibbs free energy of activation, how it affects selectivity comes from biological or ion selective biological channels. So let's look, for example, at the potassium channels, which we all have in our body and in every living organism. And this channel actually is possible to transport potassium ions 10,000 times faster than sodium ions. So the selectivity here is very impressive towards potassium. And this selectivity is due to the special binding sites you can see here in red, the oxygen group, along the channel. And according to Nobel laureate Roderick McKinnon, from his review in Science from 2005, these sites allow a transport protein to fill ions to ensure that only the right ones can pass. Okay, so the idea here is based on 2 main mechanisms. Okay, so first of all, when the ions get to the channel, so because the channel is very narrow, so they need to dehydrate and remove the water shells surrounding them. And this removal of the water shell costs energy. Okay, so this dehydration, okay, actually establishes or creates a relatively large energy barrier. Okay, then in the next step, inside the channel, when the ion enter the channel, okay, it can be stabilized by these binding sites inside the channel. Okay, it can be stabilized. So this binding site, they kind of replace the water molecules that surrounded the ion in the solution. Okay, and by doing so, they actually compensate for dehydration and eventually reduce the energy barrier of the permeation, or in this case, the enthalpic barrier. Okay, so the interactions becomes better. So the enthalpic barrier only for potassium gets better because these binding sites, as you can see here on the right, are ion specific. So they provide a perfect match based on the distances, okay, and the size of the bare ion, they provide a perfect match only with a certain ion, in this case, the potassium ion. So in biological channels, we can really see how the activation energy play a role in the selectivity observed. So after I introduced the theory and maybe the principles of how we can use it to learn more about transport in our membranes, in polymeric membranes, reverse osmosis, and nanofiltration membranes. So I will now give a few examples specifically from our lab on how we use this theory to elucidate and maybe understand we wanted to understand the mechanism that promote water-salt selectivity, which is actually the basis for membrane-based desalination. Okay, why water permeates better than salt through the membranes? Okay, so first of all, you can see here on this figure, we use two types of desalination membranes: NF90, which is dense NF membrane that can be used for brackish water desalination, and SW30, which can be used for seawater desalination. And first of all, we can see that the intrinsic permeability, okay, which is the K times D value for NaCl and water, we can see that the intrinsic selectivity of water is much higher than that of salt, as expected. Okay, and please note that the y-axis is the logarithmic scale, so the differences are very high. Okay, and then we wanted to try to explain why we see this difference, why water goes better through the membrane compared to sodium chloride. And that's we apply transition state theory, which means that we measured the permeability of water and salt at different temperatures. Okay, and you can see here the results. You can see here the enthalpic barriers in orange and the entropic barrier in red. Okay, for sodium chloride and water for the two types of membranes. So first of all, we can see that under the specific conditions that we used, okay, you can see that there are negligible differences in the enthalpic barriers for water and salt. Okay, so the differences in the enthalpic barriers cannot explain the high water-salt selectivity that we observed. On the other hand, we can see that the entropic barrier for the transport of sodium chloride is much higher than that of water. So we conclude from this specific experiment under our specific conditions that the water-salt selectivity is entropically driven, and we can try to relate it maybe to the much larger size of salt ions compared to the water molecules. Okay, so again, freedom of motion, possible microstates in the membrane are much lower for salt ions compared to water. Another example, okay, we wanted also to understand the selectivity, the mechanisms behind monovalent, divalent selectivity, which is very important, for example, for water softening. Okay, so in this case, we measured permeability of sodium chloride and magnesium chloride under, again, very specific conditions. And as expected, we got much higher permeability of sodium chloride compared to magnesium chloride. And then we applied transition state theory to try to better understand this difference. And in this case, okay, we can actually see that the enthalpic barrier is the barrier that can explain this selectivity. So we can see that the enthalpic barrier of magnesium chloride is higher compared to the enthalpic barrier of sodium chloride, and we can try to relate it to some enthalpy-related mechanisms. For example, the fact that maybe monovalent ions undergo dehydration, okay, and hop between negatively charged carboxyl groups inside the membrane more easily than monovalent ions. Okay, so we cannot go all the way and understand exactly which mechanism is responsible. Okay, but we know that it's enthalpy related. Okay, and I will get back to this issue later, and we'll see maybe how we can get deeper into the details and understand it better. So we talked about water salt selectivity, we talked about monovalent, divalent selectivity, and now I want also to show you some of our interpretation for the more challenging monovalent ion selectivity, okay, between ions of similar charge and similar size. And for this purpose, so we took a more systematic set of anions and cations, okay, and measured the enthalpic barrier for each ion and then and each anion, enthalpic barrier. So you can see the results in green, and the entropic barrier for all these ions in yellow. And interestingly, we found that the enthalpic barrier, okay, the enthalpic barrier sequence follow exactly the order of the hydration energy or the hydration strength of the ions. Okay, so for example, lithium, which has a high hydration energy, okay, compared to cesium, has also faces higher enthalpic barrier. So this correlation, okay, implies that the ion dehydration, okay, probably plays a role in the transport. And more interestingly, even is that the entropic barrier that we measured also perfectly followed the bare side, the naked side of the ions, which also imply that if the ions are naked, so maybe they underwent dehydration. So these two sets of results may imply that ion dehydration play an important role in the transport. And I put all this measurement under an asterisk, and I will get to it later. Okay, when I will talk about the challenges in the measurements, and these were results from our specific groups. Okay, but there is already a relatively large body of work in the literature. Okay, that apply the transition state theory to measure enthalpic and entropic barriers in nanofiltration and reverse osmosis membranes. And people tested different types of ions in different types of membranes, and they concluded about different phenomena. Okay, but after a careful analysis of this data from the literature and our own results, okay, we came up with the conclusion that the results in general, they show very high variation, even between studies that tested the same solutes, and even sometimes under exactly the same conditions. Okay, so results show very high variations and are also very inconclusive. So in one study, one conclusion, in another study, another conclusions. So this slide brings me to this important part of the presentation about the challenges, maybe the uncertainties, and as I said at the beginning, we can also call it problems when applying transition state theory to explore the mechanisms. And there are plenty of problems and challenges, and I decided to focus here on three main problems and challenges when applying the theory. And let's start with the first challenge, which talks about changes in the membrane, in the polymer, okay, properties when we change the temperature. Okay, so when we change the temperature to measure the activation parameters, okay, when we apply transition state theory, we change the temperature. Okay, our purpose is to change the energy of the molecules. Okay, so in general, the higher the temperature, so the higher the energy of the molecules, and the higher the rate of the reaction, because more molecules have enough energy to cross the activation energy and react. So this is the main purpose when we change the temperature. However, as we know, temperature can affect many other parameters in our process. For example, the membrane. Okay, and one noticeable example for changes in the membrane as a function of temperature is a phenomenon that's called polymer relaxation. Okay, so when we heat our system, our water, and therefore also the membrane, so the polymer chains, they also get more energy, they are more free to move, and then they can pack themselves better. Okay, and the polymer can become actually denser. Okay, so this is a side effect that happens when we heat the water. Okay, so if we expect that the change in the permeability will be something like this, okay, when we hit the water, we eventually can get something much lower, because the effect of increasing the energy of the molecules is restrained by the changes in the polymer structure. Okay, so we tested this hypothesis. So you can see here the salt permeability as a function of temperature, and we did it in an ascending temperature manner. Okay, so we started from the lowest temperature and heated the water. So, and we did it for 3 consecutive cycles. So you can see, first of all, you can see that when we heat the water, so the salt permeability goes up, okay? However, when we finish the first cycle and go back to the second and third cycle, we can see that the permeability goes down, didn't go back to the same level. And this is probably as a result of what I just mentioned, the polymer relaxation. So when we heated the membrane at the first time, okay, the membrane also became denser. Okay, so in the next cycle, we already got a lower permeability. And now again, because the increase in the permeability is restrained by this phenomenon, polymer relaxation, so the energy barrier in the first cycle will be relatively low, okay? Because the change in the permeability is not as high as we expected. And when we stabilize the polymer at later cycles, the energy barrier gets higher. And this is one possible reason for why we get variations between studies, because this effect on the polymer. And one way to minimize or solve it is actually to measure the barriers in the other directions. Okay, so we start with the highest temperature and then cool the system down. And here you can see that the cycles are the permeability for the 3 cycles are more similar to each others. Okay, because we already stabilized the membrane, the polymer, at the highest temperature at the beginning. Okay, and then we can also see that after stabilizing the polymer, first of all, we get already higher and more realistic activation barriers. Okay, and also the fluctuation is lower. Okay, so I think this is very important point when coming to apply transition state theory. I think it is very important to start measuring from the highest temperature and then go to the lowest temperature. Okay, let's move to the second challenge when applying transition state theory. And as I said before, right now, so temperature affects not only the energy of the molecules, but other parameters in the system, and we just saw how it affects the membrane. Okay, so now let's see how it also affects concentration polarization. So when we apply this simple methodology, okay, to quantify the permeability at different temperature, in practice, what we need to do in order to measure the permeability, so we need to measure the solute flux, okay, and divide it by the concentration gradient over the membrane. And for this, we must calculate, okay, the real concentration on the membrane surface, okay, Cm. Now, I believe that regardless of using transition state theory, even if we don't measure the permeability at different temperatures, it is super important to account for concentration polarization, and I still see many studies that do not account for it. And it is very important because it can change completely the conclusions. So it is very important anyway to account for concentration polarization. But when we measure the permeability at different temperatures, okay, and because we know that Cm, the concentration on the surface, or the extent of concentration polarization can significantly vary with the temperature due to viscosity effects, okay, and diffusivity of the solutes in water, okay, that changes also with temperature. So due to this effect, the effect on the overall trend, okay, between different temperature is critical for this measurement, and we cannot apply transition state theory and measuring permeability at different temperature without accounting rigorously and properly for concentration polarization. And one thing that we show in an ongoing study is that actually the best way is to try to minimize the concentration polarization. So you can see here on the y-axis the concentration polarization modulus, okay, which is actually the concentration polarization extent. So you can see that when we increase the crossflow, and when we increase the crossflow and reduce the concentration polarization, so eventually we will get more stable energy barriers, okay, with less fluctuations. So minimizing concentration polarization is also very important when we come to apply transition state theory. A third challenge that I wanted to introduce, and for me maybe it's the most interesting challenge, is related to the entropy compensation phenomenon. And this entropy compensation is actually is a repeating phenomenon. Okay, it happens very often. I wouldn't say all the time, but it happens very often, and not only in membrane science, but also in other fields that use transition state theory. And I will explain now why it complicates the analysis of the results and why it is a challenge. Okay, so first let's try to explain what the phenomenon is actually is. Okay, so we measured the enthalpic and entropic barriers for a series of anions and cations, and then we plotted the enthalpic barrier, okay, as a function of the entropic barrier. And you can see that we get this kind of a trade-off between the enthalpic and the entropic barrier. So when the entropic barrier goes up, the enthalpic barrier goes down, and vice versa. If the entropic barrier goes down, the enthalpic barrier will go up. Okay, so this is basically the compensation effect. So this also means, okay, that if there is this kind of compensation and trade-off, it also means that the delta G, okay, the Gibbs free energy of activation will be more similar between the different ions, which eventually means that we will have low selectivity, okay, if the delta G is similar. So from an application point of view, okay, this is the entropy compensation results in decreased selectivity, and this is something very worrying and disturbing. Because, for example, if you want to design a membrane that will have good interactions with a specific ion, so the enthalpic barrier will go down, but then in expense, the entropic barrier will goes up, and we will end up with a similar delta G, and the effect on the selectivity will be minimal. So this is from the application point of view, okay? But this phenomenon also raises a very fundamental, important question about the origin of this this phenomenon, of this compensation, and there is still an ongoing debate on this topic. Okay, so one side claims that the explanation for this compensation is a physical, so we can actually provide a real physical explanation for this phenomenon. So you can see, for example, in biochemistry, okay, when a ligand binds to a protein, okay, so if the interactions with the protein are better, so the interactions are stronger, okay, so the enthalpic barrier for the binding will be lower, okay, but then because the interactions are very strong, so the freedom of motion will be lower, and the entropic barrier becomes actually higher. So this is an example for a physical explanation for this compensation effect. And we have some, we can also find explanations for what we have in membrane processes, okay? But on the other side, okay, there are people that claim that this compensation effect is actually an artifact in our calculation, in our measurement. And I show you here only one example of a figure that maybe illustrate the problem, okay? So actually, when we come and measure, in our case, the permeability at different temperatures, you can see that in the large scale, when we zoom out, we actually see that this measurement happens in a very narrow range of temperature, okay? And it does not capture the entire picture, okay? So when we take very narrow points, okay, so we may expect like very high fluctuations and variations in our measurements, and we will not catch the real trend. In this case, the real slope. Okay, so eventually, using this method, we need to measure the slope for the enthalpic barrier, and we also need to measure the intercept for the entropic barrier. So if all the points are concentrated in a very narrow range, so every time that we will measure higher enthalpic barrier or higher slope, we will end up at higher intercept, which means lower entropic barrier. Okay, so this is, I mean, this approach actually claims that we have a problem with the measurement. Our measurement is not accurate enough because we actually measure something that very short temperature range. So I didn't find a solution yet for this problem in the literature, also in other fields, again, not only in membranes. And I really think that this topic needs further study, okay, to better understand and maybe solve this phenomenon. Okay, so for the last part of my presentation, I just wanted to give you maybe a glimpse of ongoing and maybe future research and needs that need to be done to improve the application of transition state theory. And one problem with the current approach that I introduced is the fact that we actually measure an effective energy barrier, okay, for the permeability that lumps within it both the energy of partition and the intrapore energy barrier for diffusion inside the membrane. Okay, so differentiating between partition and diffusion is highly needed and can be very helpful to understand the transport, as I previously showed you in the case of magnesium that showed a higher enthalpic barrier compared to sodium, but we were not sure if it's because of the dehydration and entering into the membrane or the intrapore diffusion later inside the membrane. So indeed, it is much easier to measure the permeability than to measure partition or diffusion. Okay, but one emerging way to measure, for example, partition or the partition energy is using a QCM device, okay, that can provide maybe some preliminary insights into the energy of partition. This method of QCM is not perfect, because the QCM basically gives you mass, okay, mass absorption on the membrane, and when we deal with salt in water, so we are not sure if the mass absorption, okay, that the QCM detected is based on the anion, the cation, or maybe some water molecules from the hydration shell. So we need to assume relatively many assumptions to use this tool. But still, we can get some nice and interesting trends. Okay, so for example, we can see here that the partition energy that we measured for magnesium chloride and calcium chloride, okay, for divalent cations, okay, is lower than the partition energy for lithium chloride and cesium chloride, which suggests that maybe the partition of magnesium and calcium is easier into the membrane because the membrane is negatively charged. So the compensation for the dehydration is very good, okay? So it also means that the higher enthalpic barrier that we observed for the calcium and magnesium is probably due to the diffusion of these ions later inside the membrane. Okay, so when we combine results from QCM measurements on partition and permeability measurements, okay, maybe we can have a better picture of the problem. So it is very useful to try to elucidate the full energy landscape, what happens in the partition, what happens in the diffusion, and not only in the entire process. And another main drawback and limitation of the current approach is the fact that we actually assume that our polyamide, our membrane, is homogeneous, okay? While in reality, we know that the membrane is heterogeneous. We have different pore sizes, and we have different passes that the solute can go through. So in a recent study, okay, in a recent simulation study, we actually simulated we simulated a scenario with heterogeneous membrane, which has a pore size distribution and multiple passes for permeation, okay? And we calculated the effective barrier, okay, that we usually measure, okay? And we wanted to understand what is this effective barrier that we actually measure. What does it mean? Because in the case where the membrane is homogeneous and all the barriers inside the membranes are the same, we know that the effective barrier is the summation of the partition and the energy barrier of diffusion. But what happens if there are different barriers along the pore? And then we actually found that the effective energy barrier does not represent the minimum barrier. It does not represent the maximum barrier. It does not represent the average barrier. It actually represents, okay, something that is close to the maximum barrier in the most permeable pass, okay? But my main point here is that the measurement that we perform to find the effective energy barrier basically gives you an interpretation or measurement of a single barrier in the membrane that not necessarily reflects our story, okay? And it cannot really elucidate the entire picture, okay? So the experimental effective barrier is limited in explaining transport mechanisms. So I think the next step will be to see how we can isolate different barriers in the membranes okay, and actually measure the individual barriers to better understand the transport mechanisms. And I will finish with one slide of takeaway messages. So first of all, we saw that experimental transition state theory is still, despite all the challenges, is a valuable tool to explore transport in salt-rejecting membranes. Okay, it should be improved. Some hidden phenomena, okay, like polymer relaxation and concentration polarization effects associated with the temperature-dependent measurement of the activation parameters can lead to sometimes even to false conclusions. Okay, we need to be very careful with the interpretation of the results. And as I just said in the previous slide, we will probably need soon better experimental tools to understand and quantify the real barriers or even individual barriers along the membrane. And with that, I will finish my talk, thanking the students in my group, especially those that were involved in the results that you saw. I would like also to thank some funding agencies and to all of you for joining and listening. Thank you.
Thank you very much, Razi. That was really, really very interesting. I open the floor for questions now. I don't see any questions in the chat, however, but for our audience...
There is one.
Is there one? Okay. I don't see it at the moment, Tal, so if you don't mind reading...
I will read it for Razi. So thank you, Razi, for the inspiring talk in a difficult situation.
Thank you very much.
Is there any computational method, for example, DFT, to calculate or decouple enthalpy inside the membrane?
So I think it's this question is related to the last thing that I mentioned. So if I understand the question properly, if DFT can be used to measure a single barrier inside the membrane?
I can repeat it for you. So is there any computational method to calculate or decouple enthalpy inside a membrane?
To decouple enthalpy and entropy?
He didn't mention entropy, but perhaps that's what he meant.
Okay, so I think that I'm not a simulation guy, so I'm not an expert in DFT. The main problem with these simulation tools is the fact that maybe the medium is not simulated properly. So I know now that there are a few people that know how to simulate well polyamide, okay? So specifically, I guess it is possible to isolate enthalpy barrier in a well-defined pore geometry, but I think it is still complicated for our polyamide structure. So I hope I addressed the questions properly.
I think it's good. And the second question, isn't the pressure gradient in RO and NF too high, causing dehydration of both monovalent and divalent ions? If yes, does this make the hydrated radius insignificant in transport?
So again, if I understand the question properly, is that the question is if pressure affects the dehydration of the ions, right?
Yeah.
So I think that we have some ongoing results that I didn't show here that actually suggest that no. I don't think that practical pressures that we use in the salination membranes, okay, if we talk about 10, 20, 30, even 70 bars or 80 bars, I don't think they can lead to significant, or they cannot promote dehydration of ions very negligibly.
I remember the paper, yeah, there was a paper about this, yes. So
we were also curious about it, and we discussed it in one of our papers. But these days, I more tend to believe that pressure has, of course, other effects on the transport. I think the pressure it affects more the membrane than the ions themselves.
Yeah. But this is very curious because a lot of papers they publish it in very high impact journals, but they mention that pressure gives dehydration. But anyway, there is another question asking if the presentation video will be available. I think it will be. You will answer. So there is another question. Thanks for the nice talk. I'm wondering whether the transition state theory is also applicable to other membrane processes.
Sure. So, like for electrodialysis, I guess, and any, so again, transition state theory can be applied to any process that involves elementary steps. Elementary steps mean like steps in the molecular level, okay? So diffusion, for a process that involves diffusion of ions, okay? Transition state theory can be used, okay? So because, as I said, diffusion is a type of chemical reaction because it involves breaking and reforming bonds with the environment. So again, any process that involves changes in the molecular level can be interpreted to some extent by transition state theory, I believe.
I think you are good friends to Benny Freeman and Manny. It doesn't count whether the membrane is porous or dense. Yeah? So make your friends very good connection for both parties. Yeah? That's a very good answer. So another question. Thank you, Razi. What is the connection between transport resistance and transmembrane energy barrier? I think that the transport resistance is commutative, but it seems that activation energy is not cumulative. Is it clear for you?
So maybe, if I understand properly, he asked if the energy barriers in series, can we sum them together for a cumulative barrier or something? For like to define the overall resistance, or?
My understanding is that the question is like that. So transport resistance is cumulative. So it's a bulky stuff, combine everything. But the activation energy is not. That's what he mentioned, what he asked.
So I think the answer is yes.
Okay.
So
all right.
I mean, yeah. At least the effective barrier that we measure for the entire process is not something cumulative. It's not something simple that we just sum together, okay?
Okay. Another question. Thanks for nice talk. What would be the rejection rate of anions with different charges? Is it possible to apply transition theory in this aspect?
I'm sorry again for
you talk about the anions with the same charges, the monovalent anions.
Okay.
The answer is that what about the different charges? Can you use the same theory to analyze the anions with different charges?
You mean divalent, monovalent? Or
yeah, like, exactly. Or trivalent.
I mean, so of course it can be also modeled with TST. I gave example with also divalent ions. So,
but then you have Downline exclusion effects. Will this affect your model or affect your
Downline exclusion? I think is primarily related to enthalpic effects, to the enthalpic barrier. Okay, so higher Donan exclusion will increase the enthalpic barrier.
Okay. Yeah, it's clear. Yeah. I think we don't have more questions here. I would like to thank you, Razi. I have some questions, but I will send you email later. Thank you very much for giving us a very nice talk in such a very difficult situation. We were lucky that there was no siren. So thank you again, Razi, and we will come back to Luan. Luan.
Thank you very much, Razi. Thank you, Tao. I'd like to hand over to the co-editor-in-chief of JWPE, Dr. Ludo